Right, welcome to Electrochemistry Part 3. So in Part 3, we're going to look at balancing an equation in terms of its electron movement. So this would be a redox reaction. We're going to look at it and follow the movement of electrons. We're going to use the movement of electrons to balance an equation in an acidic solution. So first we're going to look at in acidic solutions. And so what we're doing right now is we're combining the idea of redox reactions and acid-base. And we're also going to look at how do we do it in basic solutions. And so let's go ahead and we're just going to define sort of a progression of rules. Now with any redox reaction, this is pretty much always the first thing you're going to do. It's always your safest bet to start here. And assign oxidation numbers, because then you know how the electrons are moving. So let's go ahead and assign oxidation numbers to each of the elements in this reaction, seeing how they change. Now you'll notice that we have hydrogen here, and we don't have it reacting with anything. Well, it's going to react with the water, and it's going to be released into the water as hydrogen ions, making an acidic solution. But we don't really know how much or what not, because we need to balance this in terms of how the electrons move, because we know that that acids release hydrogen ions in solutions. So let's go ahead and assign oxidation numbers first. Okay, so this is what I've done. I've assigned the oxidation numbers. Hydrogen's always +1 when it's in a molecule like this. And so, so chlorine here is going to actually assume a +1 as well. Now, why is that? Well, because oxygen's always -2, right? So here we have oxygen as -2. So that means to make this without a charge, because it doesn't have a charge, it's not ionic, we see, it's going to have a +2 and a -2, so it equals out. And then coming over here to the nitrogen, we have +2, because this oxygen is a -2, so my nitrogen here is +2. On this side, my chlorine, you'll see, did make a change, because now I'm on elemental chlorine, which is going to put me at 0. In this case, I have a nitrogen that's going to be a +5, because I have a -6 total with my oxygens here, each one of them being -2, having 3 total, and I have an overall charge of -1. So if I have an overall charge of -1, that would mean I'm adding +5 to my -6. Now, your next step, what you want to do is you want to connect your matching atoms from either side with a line. This is how I do it. Just connect it with a line like this. And then what you want to do is you want to just put what the difference is. And that kind of shows your oxidation and reduction. Okay, so the chlorine going to the Cl2 went from +1 to 0. So that was a -1 change. We added a -1 to the +1 to get it to 0. The nitrogen going from a +2 to a +5 added a +3. So that's step number 2, finding the differences. And I like just kind of drawing these lines between them and then putting those right there. Now the third step would be to fix those differences with coefficients. And so what does that mean? Well, here's what it means. It means that if I have a -1 and a +3, I haven't accounted for 2 of these -1 charges. So what I'm going to say is that I need to make this times 3. If I make this times 3, right? And so like I could put a 3 right here, and then I could put a 3 right here. If I multiply my chlorine by 3, and remember this, the whole point of this is balancing this, well then I'm going to match up to my +3 here. But you have to keep in mind what that does. Look, I put a 3 here, which made this 3, but when I put a 3 here, it made this 6. And so that really doesn't work. So what I'm going to have to actually do is change this so that this is now a 6, so it matches that 3 right there. Because I can't just make this into 3 of these. They come in pairs, so the chlorine actually has to be doubled, and that means you have to actually double everything. So I'm going to have to make this, instead of just doing the easy thing, which would be making this into -3 so it matches up with this +3, I have to make this into a -6. I don't have any other choice, which means that I have to make this side into a +6. And so to make this side into a +6, we remember that there is an exchange of +3, so I'm going to double it. So that's how we add in and fix the coefficients right there. Now, the next step is to balance the oxygens by adding water. Well, what does that mean? Well, if you look on this side, we have 6 oxygens plus 2. That's a total of 8. On this side, we have just 6 oxygens. So what we need to do is we need to add 2 oxygens. So we're going to do it by adding water. So our 2 oxygens are now there. So now we have 6 oxygens plus 2 oxygens is 8. Now we have 2 oxygens plus 6 oxygens is 8. And then the last step is to balance it by adding hydrogen ions. All right, so this is in acidic solution, so we've got the hydrogen over here in the molecular form, and then on this side it's going to be aqueous. So, well, it's going to be separated from it anyhow. So we have 6 hydrogens over here, and we have 4 already over here because of the water, which means that we're going to need +2 hydrogen ions. All right, so actually in an acidic solution, because of the oxidation reduction, this is a completely perfectly balanced equation now, showing it in an acidic solution, because here's our hydrogen ions over here. Now, what do we do when we're doing within a basic solution? Sorry about that. That was awful. But in a basic solution, well, in a basic solution, what we're going to do is we're just going to add a couple of rules. And so those rules are going to go like this. I think I've got it on the next page. Yeah. So for basic solutions, so here we are where we left off before. We've got our, let's see, let's get rid of these real quick. We've got our equation initially where it started from before. We did our little exchange. We added our coefficients, and then we added our water and our hydrogen to balance that out. Now, for basic solutions, you take where you left off. So that's what I did. I just went through and I quickly showed you what we'd done before, where we got to before. So you take where you left off and you add 2 things. So these are the 2 things that you're going to add to this particular equation. You're going to add hydroxide ions, because remember in basic solution, so this is in basic solution, you're going to have hydroxides rather than hydrogen ions. So notice that you have hydrogen ions in solution right here. This is clearly an acidic solution, but we want to say what would this reaction look like in a basic solution, and how would it be balanced. So you add hydroxides to both sides, equaling the number of hydrogen ions. So, so here we have plus OH negative, there's going to have to be 2 of those, I'm sorry, 2 OH negative, right? Because we're going to equal the number of hydrogen ions, or just, just by themselves, the hydrogen ions. We have 2 on this side. It says add to both sides. We're going to do that. So 2 OH negative. All right, so now what we're going to do is the last step of this is to combine any hydrogen and hydroxide to make water. Well, notice we have 2 hydrogens and 2 hydroxides, and that, of course, always works out on one side or the other. So that's what we're going to do. We're going to get rid of that. And let's see. It must be... No. All right. Add that. And let's see. Got to find where that disappears. There she is. All righty. Sorry about that. So we're going to get rid of that now. And so now we're going to take this and we combine those 2. into 2 waters, because remember we had 2 hydrogen ions and 2 hydroxide ions. So now we have 2 waters, which actually combines right here, and so we're going to have a total of 4 waters. All right, so we're going to take that last thing and we're going to combine that down into 4 waters. And we have 2 hydrogens on this side. So now this is balanced in terms of a basic solution, because here's the hydroxide ions right there. Sorry about trying to find my layer that had the right thing.